Today we'll do an elevator problem to understand 4 different scenarios. Scenario number 1, if a person go inside an elevator and if elevator is at rest and the person is standing on a scale, then the apparent weight loss or gain would be 0. The person would feel normal. However, scenario number 2, if elevator accelerate down, then the person will feel lighter because the scale will read less mass in kilogram. Scenario number 3, if elevator accelerate upward, the person would feel heavier because the scale will read more mass. And scenario number 4, if someone cut the rope of the elevator, then person will feel weightless. So what are we trying to understand today? We are trying to understand that scale read normal force, and there are 4 different type of normal force. Scenario number 1, when elevator at rest, normal force is equal to the weight. Scenario number 2, when elevator accelerate down, normal force is less than the weight. Scenario number 3, when elevator accelerate up, normal force is more than the weight. And scenario number 4, when someone cut the rope, normal force is 0. Let's talk about the scenario number 1. And scenario number 1, when we talk about scenario number 1, what do we talk about? We talk about the elevator is at constant velocity. Constant velocity. What does constant velocity means? Constant velocity means acceleration is 0 and net force is 0. That's what constant velocity means. Okay, so velocity could be 0 or velocity could be 5 meter per second. Velocity could be 100 meter per second. Doesn't matter. So the velocity or the elevator is in constant velocity. Acceleration is 0 and net force is 0. We want to see whether the person would feel heavier or lighter. So what is the description? What is the person doing? Person is inside the elevator. As you see, the man is inside the elevator. The man is 100 kilogram. The man is 100 kilogram and the acceleration due to gravity is 10 meter per second squared. Now would the person feel heavier or lighter? Well, the person won't feel heavier or lighter is because there would be no acceleration and there would be no net force. And how can we prove that? Well, we can prove that by using the free body diagram. If you draw a free body diagram and the FG is 1000 Newton. Why the FG is 1000 Newton? Because 100 times 10 is 1000 Newton. Then Fn is still 1000 Newton, making the net force equal to the weight force. And as you know that the scale always read the normal force, so scale in this case would read 1000 Newton. What does 1000 Newton in kilogram? 1000 Newton in kilogram is 100 kilogram. So scale will read 100 kilogram. So the person is 100 kilogram. Scale will read 100 kilogram. So the person won't feel heavier or lighter. End of the case. So scenario number 1 is pretty easy. Now scenario number 2, we're gonna make the things a little bit more interesting. We're gonna make the elevator accelerating down. So let's make the elevator accelerating down. So the mass is still the same, 100 kilogram. The mass is still the same, 100 kilogram. Acceleration due to gravity is 10 meter per second squared. Elevator accelerating down, negative 2 meter per second squared. And we want to find whether the person feel heavier or lighter. Well, the person will feel lighter is because there is a apparent weight loss. How much apparent weight loss? We don't know. We're going to find out. In this case, as you know that just like the first scenario, the elevator will read normal force. Elevator will never read the weight force. So let's find out the normal force first. The weight force we know 1000 Newton. Normal force would be less than 1000. In fact, normal force would be 800 Newton. We're going to prove why the normal force is going to be 800 Newton. But let's draw the free body diagram. So this is the free body diagram. Weight is 1000 Newton and normal force is smaller. The vector is smaller is because normal force is 800 Newton. How do I know? We're going to show how I know. We're going to show the math. Okay, so let's do the math. Let's write F is equal to ma. F is equal to ma is wrong. I'm going to stop the simulation. F is equal to ma is wrong. Why it is wrong? Because it is acceleration down. Acceleration down means is negative ma. So I'm going to fix my mistake. I'm going to fix my mistake. So negative ma. Alright, so what? How many F acting at the y direction? Well, I see Fn, so I write Fn. I see Fg, so I write mg. Because Fg is mg. Fg is mg. Don't forget that is equal to negative ma. So what does that mean? That means I have Fn is equal to mg minus ma. What does that mean? I can factor out mg minus a. So now I know why I said the normal force is 800 Newton. Normal force is 800 Newton is because we see that 100 times 8 is 800. So normal force is 800 Newton. That means scale read 80 kilogram. Why does this scale read 80 kilogram? Is because the acceleration is downward. There is a net force. There is a net force 200 Newton downward. 200 Newton downward net force causing the person feeling weight loss. And how much weight loss? The 20 kilograms. So apparent weight loss is 20 kilograms. So the person feel lighter as a consequence. Now we're gonna show you the scenario number 3. When we do show you the scenario number 3, we're gonna keep the mass same. We're gonna keep the acceleration due to gravity same. We're gonna keep the acceleration of is 2 meter per second square, and let's see whether the person feel heavier or lighter. Well, I can tell you that the person will feel heavier. Why the person will feel heavier? Because there is a net force upward, and that means the scale will read more mass in kilogram. What do I mean? Well, let's show you what do I mean by drawing a free body diagram. This case, just like other case, the weight force is same. Weight force never changes. Your weight never changes. So the normal force is bigger. How much bigger? Well, normal force would be 1200 Newton. How do I know? Well, I'll show you how do I know by using Newton's second law. It's pretty obvious. So you write F is equal to negative ma. Well, F is equal to negative ma is wrong. It's because the accelerating upward. Remember that. So it's not going to be negative ma this time, because when you accelerating upward, that means positive. So F net force is equal to ma. How many forces acting at the y direction? There are two forces, Fn minus mg, because Fg is equivalent to mg. Is now what do you see? You see Fn is in this case m factoring out g plus a. So why did I say 1200 Newton? Is because 10 plus 2 is 12, and 12 times 100 is 1200 Newton, and the scale will read 120 kilogram. That means the person will feel heavier. How much heavier? The person will feel apparent weight gain. Apparent weight gain is 20 kilogram. So as a result, person will feel heavier. The person will feel heavier. Excellent. So you see the scenario number 3, and the person will heavier. The scale will read, instead of 100 kilogram, 120 kilogram. Now what happened if your best friend cut the rope? If your best friend cut the rope, that takes us to scenario number 4. Scenario number 4, we're going to try to find the normal force. So scenario number 4. So if your best friend cut the rope, scenario number 4, that takes us scenario number 4. Still your mass is 100 kilogram. Still acceleration due to gravity is 10 meter per second square. Now we're trying to find the normal force. What is the normal force? To find the normal force, let's draw the free body diagram. Weight force is still same. Fg is equal to 1000 Newton. Normal force is 0. Why the normal force is 0? Because you are free fall. So what would the the scale be reading? Scale would be reading nothing. Scale would be reading nothing because since scale always read the normal force, so scale will read 0. Scale will read 0. What does that mean? That means the person will feel, what is the apparent weight loss? Apparent weight loss. Well, if the scale would read 0 Newton, and if the weight is 1000 Newton, the apparent weight loss is 100 kilogram. What is the consequence? The person will feel not lighter, the person will feel weightless. Thank you for watching.
Subscribe to Barry Science Lab! Subscribe to Barry Science